right, sure. So I'll just start. Hi, everyone. Basically, good morning. It's morning in here. Good afternoon in other times. So I'm Dr. Sarbana Sopan Sarbandi. I'm Faculty of Mechanical Engineering at University of Missouri, Kansas City. I'm also Director of the Advanced Renewable Thermal Energy Laboratory here in UMKC. And today's presentation talk is about heat transfer enhancement and optimization analysis of energy storage-based solar thermal collector. So, the outline of today's talks, first of all, I would like to talk a little bit about the solar market insight that we currently have all around the world, and specifically for United States. Then I will just introduce you what are the solar water heater technology and what is the motivation for this study, for this part of the research project, and which is focused on the evacuated tube solar collectors. So this study is focusing on computational fluid dynamics modeling of a solar collector, and there are two phases that we consider for this analysis. This is an optimization analysis of a commercially available collector. In phase one of this study, we are considering the effect of heat pipe position, where in the second phase of this study, we are trying to analyze the value integration of various types of PCMs. So what are the solar water heater technologies by themselves? First of all, just getting to the solar energy industry, it's good to know what are the solar market for that technology. So that would gives you the room to grow, and then as well as just gives you motivation how you can apply it in different geographical locations. So in the United States, basically, we have around 108 gigawatt of the solar power already installed, and we are expecting to have the value of the US solar market in 2020 to be $25 million. So we are predicting that there would be a growth over the next 10 years. So by 2030, we would have 30% electricity generated by the solar. And so nowadays, we have over 4% of the US electricity coming from the solar energy, which is more than 80%. 80 basically tons than its share a decade ago. So for sure, these percentages are different in European countries as well as the US. And specifically in the state that we are studying these analysis, which is in Missouri, we do have around 278 megawatt of the power solar installed. And the national ranking, unfortunately, it's reduced over these couple of years ago. And we are currently number 32 on the national ranking. So if you take a look at the capacity that we are holding on this curve, it shows that in 2014, we do have like the much capacity installed in Missouri. However, over these past 5 years or so, we do have the reduction. So now we are again getting back to the where we were 5 years ago. So we are expecting to have a growth projection of 485 megawatt over the next 5 years in Missouri. So what is the solar water heater technology? The main component of this technology is a solar collector. Solar collector is absorbing the sun radiation and pass this radiation, but once it's absorbed, to the water which is circulating through. This water later on is stored in a storage tank, so you'll be able to use this hot water during like longer period of time for doing any household activities such as taking shower, or you can use it in the commercial buildings which produce the hot water for your activities. So this demand side can be different based on the application. However, the storage tank, the well-insulated storage tanks, they will lose this heat eventually. So whenever you would like to use this water for let's say 7 or 8 hours after the sun is gone, your stored tank, it may not have the enough temperature that you're looking for. Therefore, most of these technologies, they do require a booster unit which utilizes electricity or gas to heat up this water so it reaches to the temperature that you're looking for on the demand side. However, then what would be the point? We are trying to utilize the green source of energy and use it for replacing by the coal or the electricity generation thing. And however, this booster unit is now a troublemaker. So on the right, you would see that this is like integration of different types of the collectors for this type of technologies that you can have it at the residential houses that I will explain in detail of how these collectors look like. So there are millions types of, not millions, but there are a bunch of types of the solar collectors that you can apply in this technology. But the focus of this study is utilizing evaporative tube solar collectors, or in short, ETC. So ETC, it does have its own specific geometry configuration that helps it to have a higher efficiency. As you can see in this figure, ETCs are two concentric tubes that they are infused at the end. And then within these two concentrated tube, we do have a fin, which is like a thermal conductive material to transfer this heat. And then within the collector, we have a copper heat pipe, which basically its responsibility is to transfer the heat, which is absorbed through the collector, and pass this absorbed heat through the evaporation of the small droplet of the water or glycol to the water, which is passing through this manifold. And basically, it's just converting the sun radiation to the heat, which is passed through this manifold, but later on, we just absorb and stored in your tank. So between these two concentric tubes, there is a vacuum region. This vacuum region will eliminate any heat losses. So that's why it makes these type of collectors more attractive. Also, due to the round geometry of these types of collectors, we would have passing tracking of the sunlight. So anytime from the morning till the afternoon, you don't need to use any tracking system or so. It basically by itself, by the geometry of the collector, it absorbs the radiation and do the passive tracking by themselves. So around the world, there is a very great interest on using of the evaporative tube collectors, around 81.9%, whereas the other types of collectors, such as the flat panel, they are around 14.7%. However, in United States, ETCs are not well known. Therefore, the usage of the flat panels are around 77.8%, and there is only 1.2% usage of the ETCs. So there is a great market for ETCs to just have this exponential growth. Motivation of this study, I already talked about what is a booster unit. So basically, booster unit use the electricity all cold, so which is not interesting for having a fully green energy. So the motivation of this study is trying to eliminate the need of a booster and then try to have a backup source within the collector, which is also kind of like can be part of the green technology. If you look at the figure on the left, this shows basically the daily residential water heater demand in summer and winter mode. It shows that during the 24 hours of the day, the morning peak zone, it's a start around 6 a.m. till around 9 or 10 a.m. And the evening peak zone, it's a start from 5 p.m. till like 9 or 10 p.m. For sure, meeting the demand of the morning peak zone for both summer and winter, that would not a challenge because we do have the sun radiation available, and then we can provide the hot water for doing such activities. However, take a look at the evening peak zone. Starting at the 5 p.m., we may have not sun radiation, especially during the winter time. So this study in here, and just part of the research work at my lab, is trying to meeting the demand of an evening peak zone without usage of a booster unit through the integration of the latent heat energy storage materials, which they are also called phase change materials, which if you know them, these are the type of energy storage or type of materials that they go through the phase change process when they do the melting solidification. So as soon as this material, it heats up, it starts melting within a rigid body shell. When it's melting inside this rigid body, as you can see in this video, this melting and solidification may not be visible to you. However, when it's melting, it is absorbing this energy through this melting process. And once the temperature drops and it's cooling down, it sends back this energy, this stored energy to your system. So you can assume that if you apply this material within your collector, or normally, we do have a couple of studies that they applied it in the storage tank. If you apply this material within your system, once it's heat up and do the melting process, and when the temperature drop, it can now heat back your system like a booster unit within your system. So you're not using the electricity or coal generations. So one of the most important basically tools that can gives you the how the system perform and the feasibility of your proposed work or proposed technology is using the CFD modeling. So the CFD software that we are used for this analysis is the ANSYS Fluent, and we do have like couple of for sure motivation that why we are moving with the CFD analysis. Based off the rapid change in the weather conditions, as well as the high cost of the installation and maintenance, and the material degradation, for sure talking about the PCM, all of these helps us to get a better insight of how the system perform through the CFD modeling. So the CFD analysis will give us the detailed insight of the thermal behavior, how all of these parts move together basically within the system, and it also predict the melting fraction of the PCM. So I mentioned that we are integrating the PCM within the collector. However, due to the having a black absorber layer on the collector, which is basically working as the absorber material, we are not able to see the inside of the collector, so experimentally. So that would be hard for us to figure out that if PCM is fully melted or what's going on inside, because we had a couple of issues previously that we left the system outside and for summertime, and we did not know what's going on inside the collector, and then it was overheated, the system was not cooled down, so therefore it started overheating the system, material start degrading, and then we had the leak from the collector. So that's not what we are what we need to have in any experimental work. So the novelty of this work is modeling of the HVAC integrated with PCM within the tubes, and we developed a user-defined function, a UDF, to implement the various solar heat flux throughout the day. And then we studied this thermal behavior for 24 hours of the operation to literally mimic the experimental work. And we do need to figure out the optimization part, which is the effect of heat pipe relocation, as well as effect of the different PCMs. So this figure on the right shows the basically mesh of these one tube of the evacuated tube solar collectors that I will just get into details of it in a moment. So we are considering that on a steady simulation, one HPETC in short, and what I call the HP is the heat pipe. So we do have different types of the evacuated tubes, but they are not having a heat pipe, and they are called U pipes. So in this scenario, we are just having the commercially available heat pipes where it was the heat transfer happens through that evaporation condensation that I mentioned. So we consider constant properties of the PCMs. We are considering the Bose-Noakes approximation. We do have the laminar and incompressible flow already considered. We are considering there's no heat loss or heat gain through the collector. For sure, that will deviate a little bit from the experimental work. I mentioned that ETCs, they do have a vacuum and the rate of the heat loss is low. However, there are a couple of others, heat gains and losses through the system. So we would have a little bit of deviation from experimental work, and we are considering that heat pipe is as a high thermal conductive devices. So we consider the simple scheme for velocity pressure coupling, second order up-in differentiation method was analyzed, and the Prosto scheme was analyzed for this type of analysis. We considered all of our boundary condition the same as the experimental work because the experimental work was done earlier, the earlier stage of this study, and then we performed the CFD modeling, so we do have the cross-validation that happened throughout this stage, and then all the other boundary conditions are the same as what we have in the feasibility analysis. So once a big model of the system is analyzed, which was part of the other work of my group, now we are trying to study how we can better enhance the performance of the ETCs. So commercially available ETCs, as we started talking about it, they do have their heat pipe located at the top surface of the ETC. However, we were trying to figure out if we move the heat pipe to the center of the ETC, how it affects the thermal behavior of the collector and how it affects the melting process of the PCMs, which is inside the collector. So this also shows that discretized geometry of the heat pipe in ANSYS Fluent. So in this phase, which is phase one of this analysis, focusing just on the location of the heat pipe, we already applied our boundary conditions. For sure, we need to have the solar radiation data as the input to the systems. So we do have the Kansas City weather data, solar radiation, around about 24 hours of the day for 24 hours in a day. And then we applied all of our other boundary conditions that I have already discussed. So we needed to do the grid independence check to make sure that our results is reliable. So we did the grid independence analysis, and then we look at the liquid fraction to make sure that the grid that we have is just perfectly fine for this optimization analysis. So the results that it shows in phase one, which was just the effective heat pipe for the collector, it shows that the optimized HPETC, it means that when we consider the heat pipe located at a center, and the conventional HPETC means that whenever you have the heat pipe at the top. So what we have in here, what we saw in this result, we saw that we have 24% higher melting fraction of the PCM within the collector when the heat pipe moved from the top to the center of the collector. And also, we take a look at this is called under the normal operation, and just I forgot to mention, the normal operation means during these 24 hours, all the time the pump is working, meaning that, for example, you're at home and then you wanted to have the hot water, so you're extracting this heat for 24 hours. However, stagnation operation or a stagnation mode, which you see the result on it on the right curve, meaning that you're not home for a long period of time. Let's say you went to work, you got back around 5 p.m. or so, and that's the time that you would like to do any household activity or you take shower. So right away you start the pump, meaning that throughout the day your collector was absorbing the heat without any cooling process, and suddenly you start the pump and the pump start running and releasing this heat. So the figure on the right is showing the stagnation operation, and it shows that our proposed technology can have the delta T liquid fraction of 48 minutes. So that's a great thing that we can see whenever we are dealing with the PCM. So it delays basically the amount of the stored heat. So as we mentioned earlier, CFD modeling gives us the insight within the collector. So I don't need to experimentally dig into the system, and CFD modeling providing me the correct insight of how this melting and solidification happening. So these two figures, where on the left we do have the conventional system and on the right we have the optimized or proposed design in here. It shows how the melting process of the PCM happening, and as you can see on the right, we have a much better liquid fraction, and we have much better of this phase change process happening. And as you can see at 1 p.m., we have our system fully melted. I mean, the PCM is fully melted within the collector, which helps me to store energy faster, as well as it kind of delay the amount of the delay the release of the heat on the other side as well when the system start cooling down. So in phase two of this study, we focused on, now we talked about PCM, and now we said that, excuse me, and also we said that, all right, now I figure out if I move my heat pipe from the top to the center, I would have the better thermal distribution within the collector. However, what are the options, what alternative types of PCM we can integrate within these collectors? First of all, whenever you talk about phase change materials, and you would like to apply those in larger scale applications, there are certain criteria you need to follow. These PCMs needs to be inexpensive. For sure, the cost is the first thing that any customer is concerned about, as well as it should be non-toxic when you apply it to any residential or any commercial buildings. You need to make sure that you are not provide any toxic material. So therefore, we ended up choosing three types of the PCMs, namely tritiol-contained paraffin, which you can see the figure in here. This is literally the candle wax. So this is very similar to the material that you have it in your candle, and it has the melting point of 72 degrees C. We have erythritol chosen. Erythritol is exactly a sugar sweetener, so it's what you have in your coffee, so it's widely available, non-toxic. And xylitol is also another sugar alcohol. There are different criteria or different property differences between these type of phase change material. However, All of those are widely used in food industry or pharmaceutical, or they are all non-toxic, non-corrosive, non-flammable, and then we can use those as the high latent heat storage materials. We do have the properties, all the thermophysical properties of those materials selected, and then we know that among these type of PCM, erythritol, the sugar sweetener, it does have the high thermal stability, meaning that there is no change in the latent heat of the erythritol after 1,000 test cycles, meaning that after heating, cooling, back and forth. However, xylitol showed less than 2% drop in the melting enthalpy after hundreds of the test cycle. So all of those are viable and reliable sources that you can integrate within your collector. So we apply different types of the PCM with the collectors, and again, we try to look back how the liquid fraction happening under the normal operation and a stagnation operation that the results are showing on the next slide. If we look at here on the liquid fraction under normal operation, we could see that our tritiol-contained paraffin, it does have a higher melting fraction of the PCM, and that depends on the temperature that we are dealing with. If we go back to the temperature or melting temperature of these types of materials, so the tritiol-contained paraffin, it does have a 72 degrees C melting, so it is melted faster, or it reached to its melting point faster than the other types of the PCMs, and that's why we can have a higher liquid fraction. However, if we take a look at this curve, which shows the amount of energy that is stored within the collector, we would also still see that the tritiol-contained paraffin, it stores around 295.39 of the kilojoule per kilogram energy stored within the collector. However, the maximum fin temperature, which is the tube temperature, is higher for the xylitol, which is around 357 Kelvin. So we run the system for the stagnation operation as well, meaning that there was no cooling happening, and if we were just heating and suddenly we start the pump, we see in this scenario the total energy stored for the erythritol was around 413 kilojoule per kilogram. So that also meaning that you stored more amount of the energy within the corrector that it can be released later on. And if we take a look at the fin temperature or the tube temperature, we would see that we had the 10 degrees C higher temperature for the fin for the operation of the normal operation on the xylitol tube. So overall, we concluded that by doing this analysis under a stagnation operation, which was an on-demand operation, the solid to liquid phase change process was expedited by 48 minutes whenever we talked about this proposed design where the heat pipe moved from the top to the center of the glass tube. However, during the normal operation, the maximum liquid fraction of the PCM was reached at 98% in the optimized system, basically compared to the conventional, which we only reached to the 74%. And the reason is, as we discussed, when we move the heat pump from the top to the center, we have better heat distribution within the collector, which helps the PCM to melt it uniformly, rather than one side, which is facing the sunlight, melted, the other side if they're just in solid phase. So that won't give me the better heat distribution or energy storage. In phase 2, when we just talked about the different types of phase change materials to be integrated, under the normal operation, we saw that the tritiol-contained paraffin, it exhibited the total energy among the others at the highest of 295 kilojoule per kilogram per tube. However, the xylitol, it has the 10 degrees C higher temperature, the tube itself, higher temperature due to the high specific heat capacity of the xylitol. And in a stagnation mode, on the other side, we saw that the erythritol, it exhibited high amount of energy storage, and the reason is melting point of erythritol is 118. Whenever we are talking about a stagnation or on-demand operation, your temperature is just overheated without any cooling. So erythritol reach its melting point, and that's why it was fully melted during that operation. Whether in normal operation, we may not never reach to the 118 C. And also we saw that the tube integrated with the xylitol shows higher fin temperature at each time step. So we are recommending utilization of the paraffin xylitol in normal operation whenever you know that your pump is going to run for 24 hours, and the erythritol xylitol in on-demand operation to have the better system thermal performance. So this shows like my undergraduate, graduate, and like PhD master students and a couple of the alumni. And RT Lab quote is just, today is our turn to make the world sustainable. So thanks for your attention, and I'll be happy to answer any question now. And you can contact me by my email if you have further